once it's going down, another header is added. So if you remember the example of philosopher, translator, and secretary, so for each layer that the data is going down, one layer in the actually bottom, one header in the bottom layer is added, and this means this header is provided services for the upper layer. And here the data is coming down, and here we have the physical layer that we talk about this, and now the data is going up, so the layer here is, the header here is omitted, and here we don't have any header until the application layer that one message actually is transmitted. And these are the details of the layers. So at the very bottom, we have the physical layer that during this lecture, we will talk about the details of this physical layer. And the second layer here is data link layer, network layer, transport layer, session layer, presentation layer, and application layer. And these are the 7 layers that during this actually model, reference model, during these 7 layers, we can analyze the system in an easier way. And each layer, of course, has its own protocols and details, and this is the structure of this module. So during the rest of the module, we will talk about each layer in great detail and what is happening actually in each layer. So here you can see we have 2 hosts. One is sender, and the other one is receiver. And these are 7 layers for this type of model, reference model that we want to take. And each layer has its own protocols and services and details that actually we see what is happening. And this is for OSI reference model. So as I mentioned before, the 3 layers in at the bottom. So these are regarding the physical networks, and router actually exists here because if you remember, the main task of router that was taking the information from one part of the network and pass it on to another part of the network. And these 4 layers actually is regarding application. But in the following, you can see the responsibility of each layer in detail. And here, we have, again, suppose this is A, this is sender, and this is receiver. And these 3 actually is regarding physical layer. And once the data is passing down, this is the actually flow of the data. And now this is the physical layer. And now the data is going on until here that we have some things actually disappears. But briefly, I want to talk about the responsibility of each layer. But in the next lectures, for each layer, actually we have one lecture note or half a lecture note, and we can talk about them in great detail. The physical layer that I will talk about it during this lecture, so is a layer that actually we define the electrical and mechanical and every physical medium that we can use for the transmission. So this layer is responsible for activating the physical link. Physical link means it could be a cable, right? Activating this physical link between end systems and maintaining the physical links. And once the transmission is finished, so deactivating the physical link. So this is the main responsibility of physical layer, but of course there are many things in between, and we will talk about that. And it deals with voltage levels, timing of voltage signals, physical data rates, and so on. So this is a quick introduction, but for each of them, so we will talk about them. But what about the second layer? So this is data link layer. And in this layer, actually, transmitting the data is happening. So this layer is responsible for the transmission of data between adjacent nodes. So if we have, for instance, one node here, node A, node B, and node C, so the transmission of the data between nodes so happens here between any 2 adjacent nodes once we want to transfer the data. So this layer is responsible for the transmission. And of course, yeah, there are some things in between that we will talk about this. For instance, process acknowledgements, and also detect and recover from damage, and make sure the transmitted doesn't drown the receiver. What does it mean? This means actually make sure to not overwhelm the receiver with too much information. So this is another responsibility of this layer, and control the access to the medium in broadcast networks and so on. So the third layer actually is network layer. And what is the difference between network layer and the previous layer, the data link layer? The data link layer actually is responsible for transferring the information between any two adjacent nodes. But here, network layer only cares about the sender and receiver, not any intermediate node. So if we have, for instance, A here and B here, so if we have some intermediate nodes, so in between, so this network layer doesn't care about these nodes, and just the main responsibility is about the transferring the data between A and B, between actually sender and receiver. And another responsibility, determine the route, actually define the route actually for this transmission. So based on the topology, in the topology, maybe there are many routes. So which route should be established so the network layer is determined, and perform congestion control, and also overcome the problem of interconnecting heterogeneous subnets. So what does it mean by heterogeneous? Once we have the combinations of different platforms, right? For instance, here, LANs and WANs and other actually platforms, so those would be heterogeneous, and each of them has its own protocol. How we can put together these actually heterogeneous subnets and come up with a network? So this is, again, the main responsibility of a network layer. And here we have a transport layer. So this is the real lowest end-to-end layer between source and destination, because the bottom three layers is regarding network. This is the fourth layer. This is the lowest end-to-end layer. And for instance, yeah, these are some details that we will learn about them later on. But here, for instance, the main responsibility of error detection and error correction, so would be in this responsibility of this layer. And regarding this error detection and error correction, in the current lecture, I will deliver some slides. And this is the session layer. So the token management happens in the session layer. For instance, who can have the access to the shared resources? Or if there are some interruption in the network, so we should start from where? So where were we before, and we should start from where? So this is the responsibility of session layer. And presentation layer, so this layer is not regarding the transmission of the data. So this is regarding the syntax and semantics of the data. This syntax and semantics means some rules and some mathematical definitions that we need to have in our protocols. So this comes with the presentation layer. And this is application layer. This is the toppest layer, and everything that is related to applications. That could be, for instance, for file transferring, for electronic mail, which is email, or for web or e-commerce, and everything regarding application, which is the final goal of transferring data. So this comes with the application layer. But for each layer, we would have some actually lectures, and we can talk about them. But another model, so the previous model that was OSI, there is another model which is common also in this model in the literature. So this is TCP/IP. It stands for Transmission Control Protocol with the Internet Protocol. And what is the difference between this model and OSI model? So the main difference is this model is presented in only 5 layers. And these 2 layers are not present here. So the presentation layer and the session layer are not present here. And the task of these 2 layers is shared actually with other layers. This is the main difference. But in this actually course, we are mainly working with this OSI layer, OSI reference model. And this is some protocols for this TCP/IP. So, for instance, here you can see these layers, physical and data link, 2 layers are corresponding to the networks, and the remaining 3 layers on the top are corresponding to the protocols. And we already know that 2 layers, session and presentation layer, are already removed from this model. So these are some models. You can assume these are some tools, some virtual tools that can provide how we can analyze the system better. Maybe, for instance, you are saying, okay, I can add another layer and make the analysis more easy. So this is another model, right? But among different models, these 2 models are very common for the analysis, and they are widely used in the literature. Okay, this is the summary of the first lecture. So we learned about some fundamental concepts of computer networks, and also network hardware with these subsets and network software. And reference model, up to now, we know a very quick overview of actually reference models, and also this network hardware and software as the introduction lecture, right? Now, we want to move on to the details of each layer. Sorry. Okay, let's start with the details of the first layer from the bottom, which is the physical layer. And during this lecture, so I will talk about the transmission media. So which media in the physical layer we can use for the transmission. This is actually, we can see the electromagnetic spectrum for different frequency of the wave. And also different media, which is here, for instance, twisted pair that is widely used in internet, coaxial cable that we can see actually how this is actually manufactured. And this coaxial cable is very common for the TV cable. And power links that we have everywhere, including this room. Fiber optic cable for the highest speed communication, and some Wi-Fi communication based on radio technology. These are the transmission media, but we have transmission methods, how we can work with the binaries. So in the previous session, we talked about this. So actually, we are working here with a digital platform, right? How we can use the binaries and how we can transmit the information. And we would have some, finally, error detection and correction. So if the sender wants to send a piece of information as a sequence of binary, right, as a sequence of 0 and 1, maybe the receiver receives the information so in a wrong order. For instance, if you are sending 0011, maybe the receiver is receiving as 0010. So one error here happens, and how we can detect this error and how the receiver can correct the error. Okay, but you can see here the electromagnetic spectrum. So at the top, here you can see the different types of waves based on different types of frequency here. And here we have different types of technologies. So given the different types of waves, so these technologies can be used. For instance, if the wave is radio or microwave, so up to here, so you can see the technology that we can use is twisted pair, that I will talk about it, what is twisted pair, or coaxial cable, or for instance, maritime cable or radio that we can use for this range of frequency. So the range of frequency determines the type of the wave that we are working with. But here, if we are working with infrared, so here, for instance, you can see now we can work with satellite or terrestrial microwave. And this terrestrial microwave is just a simple technology for transferring the beam radio from one antenna to another antenna. But here for ultraviolet, so we can go for fiber optics. And this fiber optics, the good news here is, this is for high-speed communication. But of course, work with the wave, actually with this range of frequency. So for this range of frequency, we can work with fiber optics. And these are the exactly technologies. And here you can see low frequency, medium frequency, high frequency. And when the frequency is higher, so for instance here, so the data bandwidth is also higher. So what does it mean? Once the frequency is higher, this means we are able to transfer more data. And that's why we are interested in working with the wave with the more frequency. So these are some general information that you need to know. But let's see the details of each medium here. For instance, twisted pair. What is twisted pair? So for twisted pair, this is, you can see there are two parallel cables, but those are twisted to each other, okay? This means twisted pair, and why we twisted two cables to each other? Because the main problem in data communication is the noise or interference. And once these two cables are twisted together, so the magnetic fields induce the currents in the opposite directions, and this allows us to reduce the noise. So this is the main benefit of this. And this is used for printer cables and telephones and for small scale distances. So, and of course, there are some shields here. We can even use some additional shield, and this additional shields helps for preventing any external interference. For instance, suppose there is another cable close to this cable, and the magnetic fields doesn't affect each other, so this external shield can help here. So here we can have the transferring the information in one side or two sides. So for instance, here telephone is two sides, or internet cable is two sides. And also this technology is very old, so around 100 years, but it still is very common and very useful that we are using. But there is here another medium. This is coaxial cable, and you can see the ingredients of coaxial cable. So there is a copper core, and the core here has the main responsibility of the data transmission. And there is an insulating material here. There is some braided outer conductor and some protective plastic covering. And the main reason for adding these insulating materials, conductor, and this covering is to, again, to actually protect the cable from external interference. And you can see here, again, we can reduce the noise using these three type of actually covering. And traditionally used this type of cable for Ethernet LANs, and the bandwidth, the data bandwidth is very good. So you can see 1 gigabit per second over 1 kilometer is the data bandwidth. But the problem of this type of medium is this is very expensive, because you can see the manufacturing, so 4 different levels of materials we need to put together to build such a cable. This is very expensive, so we cannot use for the long distances communication. And that's why this is for TV cable, so we always use this because this is a short distance. So this is another one, power lines, which is, we know that, so in every room we have this power line. And there are some here plug-in sockets, and the power signal here for this power line, so the wavelengths here you can see is high, but once we want to transfer the data, so the wavelengths of the data signal here is low, and this is used for household electrical wiring, so everywhere we can see these power lines. But what about the fiber optics? So this is used for high-speed communication and is very useful. And the fiber optics, so to give you some idea, works with the light. And how does it work with the light? So there is actually glass tube. So I will show you in the next slide. There is a glass tube, and here in the boundaries, so we have some reflective materials in the boundaries. And these reflective materials are exactly like a mirror. And once the light is passing on the tube, so based on these reflective materials, so the light is reflected from here, so to another part, again is reflected, and so on and so forth, right? And this is working by ensuring that the light is trapped by total internal reflection. And why this should be reflected? This is the technology that is used to actually transmit the light. And during this technology, they can work with the light and transmit the data with higher speed that I mentioned. Actually, this is used for higher speed communication. But you can see the details of each fiber optic. So there is a core of glass. And again, this core of glass is the main responsible for this transferring the data. And two inner and outer layers, so there are in this core glass. So the boundary that I was mentioning, so this is in the boundary in the outer layer of this core glass. And we have some cladding, so glass, and some jacket, which is plastic. But if we want to have, the speed here is very high, but if we want to have a high actually boundaries, so here we need to put together 3 of them and pack 3 of them in a larger cable, as you can see here. And this gives us very good boundaries. So this is hundreds of gigabits per second over hundreds of kilometers. And this is very high, and the best things that actually is provided during the recent years. But this is another type of communication, radio transmission. So this depends on the frequency so that we are using. If we are using with very low frequency or medium frequency bands, then the radio waves follow the curvature of the Earth, as you can see here. So there are some base stations with some antenna. And if we are working with this type of ranges of frequency, now this is the way that actually the data is transmitted. But if we are working with high frequency, with short wavelengths, now actually we can use this ionosphere. And what is ionosphere? Ionosphere actually is the layer of the sphere that is full of ion, but this is eliminated from the electrons. And now this is a very nice platform for transferring actually these radio beams using this ionosphere, but only works with this high frequency. And for instance, one applications of this ionosphere transmission is defense systems. So for defense systems of each country, so this is very common for the radio transmission. And of course, we have some satellite communication. So there are different type of satellites. So you can see here, we have GEO, MEO, and LEO. And the technology of manufacturing, of course, is different. But these are defined based on their altitude from the Earth. So this is the distance from the Earth. And if the satellite is located in this distance from the Earth, so of course in this range, so this is called GEO, stands for geostationary orbit. And you can see for this type of satellite communication, the latency is 270, which is a little bit high. And the reason is because the distance from the Earth is too much, so the latency is high. But the good news here is that we only need 3 of them for the global coverage. So because the distance is very high, so by 3 of them, we can have a global coverage for the communication. But if we are working on this altitude, so we can go for this medium Earth orbit. and this is another type of satellite. So the latency latency is much less than the previous one, but the number of the satellite is more than the previous one, because now the beam range actually for this MEO is shorter than the previous one, and because the actually distance from the Earth is lower than previous one, now we need more of them to actually cover the whole area. But of course, the distance is lower than previous one. Now the latency is better than the GEO. And this is LEO, which is very common. So this is low Earth orbit. So you can see the latency is almost negligible. So 1 to 7 milliseconds. But we need the 50 of them for instance, global coverage on the Europe. And this LEO, for instance, Starlink for this satellite communication by Elon Musk, so using this LEO satellite. And the good things here is this LEO satellite is very nice for the real-time communication. So the latency here is very small. So for the real-time communication, this is a very, very good platform. And even in mobile networks that I will show you in the next slide, so this LEO is used for the mobile communication. But this LEO, so suppose this is the sender and this is the receiver. So one message needs to be passed from the sender to this receiver. How the message is passing on? So the sender actually sends the message to the nearest satellite to the sender, which is this satellite. Now this satellite passed the information over this satellite. So, and this passed over this satellite, and this is a ring topology, right? This is a circular ring topology, and the information reaches here until the nearest satellite to the receiver. And now the information actually is passed to the receiver via the nearest satellite. But this is only one type of communication based on the ring topology. But another type of communication is this. So again, the sender sends the information to the nearest satellite. But this time, the nearest satellite passed the information to the closest, actually, ground station. It's not working with the satellite again. And now this is ground station. This is another ground station, and now this ground station sends the information to the satellite nearest to the receiver, and receiver finally receive the information. These are two types of information that is passed, and this LEO is very common and very useful for the mobile networks. Okay, now let's see what is happening in mobile phone networks very briefly. So in mobile networks, we have some terminology. One actually is called cell, and another one is cell tower. But what is cell? Cell is some hexagon area. So this is the partitioning of the area, right? Suppose we want to partition this class. Now using this hexagon, we want to partition, and for each of them, we can actually talk about specifically that area. So this cell is simply some area. This is hexagon. But in each cell, we have some triangle, and this triangle is the base station. This base station is corresponding to the cell, right? In the number of the cells, we have these base stations. And suppose this is the mobile device. So once we want to make a call or, I don't know, send a message, so this mobile phone actually is trying to be connected actually to this base station, to the base station including the cell. And now, based on this base station, some communications happens. But if you, suppose here, for instance, you are here, if you move around different cells, for instance, you are walking and talking actually with the phone. So for instance, here, you see once you go from this cell to this cell, this base station should be switched to another station that is responsible for the current cell, right? And this switching is controlling network hands over communication to the adjacent base station automatically. So you don't realize actually this issue. But sometimes you are saying once you are walking and going from one place to another place, so actually the connection is interrupted. And the reason is that once the switching is happening, so the new cell is not recognize the signal, and there is some problem in the switching between two different base stations. And this is the big picture of the mobile phone network. And you can see here, for instance, again, another switching happens. But this is the more details. So here we have GSM. It stands for Global System for Mobile Communication. So here we have the mobile devices and, of course, some SIM cards. And we have some cell towers that there are some antenna. You actually can see these cell towers in the city. And this base station, so put together. So the communication between each cell and each cell phone and the corresponding cell is using this base station. And now we have some BSC here, which is actually stands for base station control. This base station control is exactly taking over the automatic switching between different cells. So once you are moving around, so this automatic switching between different cells, so comes with this box here, BSC. And we have another box here, MSC, actually stands for mobile so switching control. So this mobile switching control is a collection data points of this BSC. So this BSC for each, for instance, let's say here you have 10 cells. So for these 10 cells, for switching, automatically switching between 10 cells, so this BSC is responsible for. This BSC is responsible for another number of cells in another area for switching between the cells. And now the collection of them, actually there are some supervisors, some header for that do some analysis and control them. This comes with this mobile switching control. And now this mobile switching control itself is connected to a PSTN that stands for actually public switch telephone number. Public switch telephone number. And now this public switch telephone number actually could be connected to satellite or another source of other networks for mobile communications. And there are two other blocks here. For instance, this VLR, which is a visitor, actually location register. So for each of these blocks, there are some responsibilities. So I don't expect you, of course, to know them. Just I want to give you some intuitions. For instance, this visitor location register is responsible for roaming services. So if you want to use the roaming services, so this is responsible for. And here we have HLR, which is home location register. And this is responsible for the information of each user. What is the address of the user? What is the status of the mobile of the user? And other things actually comes with this HLR. So this is the global system for mobile communications. And here we have different generation of the mobile telephone systems. So 1G is actually established at 1981. And at that time, just we could transfer the voice with an analog services. The analog service actually, the signal that was continuous. And the implementation of analog services, not for mobile systems, in any actually platform would be difficult, the maintenance would be high, and the real-time implementation maybe is not possible. So there are many problems with the analog services. But at 2G and the second generation, you can see at this year, so that was changed to digital voice. Now, at this year, so they were working with binary variables, with 0 and 1. And now I will show you later on. They switch between 0 and 1, and everything is presented using a digital platform like the computer architecture, and everything that is using with this digital platform. But at that moment, just they could actually transfer the voice using this digital platform. And the third generation, so 2001, so this is the similar things, but on top of it, so the data also could be transferred using the digital platform. And the fourth generation, that was a very nice generation, and this is reliable, so everybody actually works with this type of 4G. So again, this is similar to the previous generation, but we are able to transfer lots of data. So instead of some limited amount of data, here lots of data could be transferred. And the 5G, that is very hot topic for the research nowadays. So the difference between 5G and 4G actually is, again, the similar platforms, but the speed of this 5G would be extremely high. So this would be almost 100 gigabit per second. And as the mobile network, so 100 gigabit per second is very high. And by this 5G, even in the future, one expectation is this 5G would be replaced for the home services. So we don't use any LAN services for the home, and we use 5G at home, because this is extremely high and can actually solve any expectation. Okay, up to here, we had the transmission media. But what about transmission methods? So with which methods actually we can transmit these data? So to give you some very quick interview. So we have simplex and duplex ways of transmission. So in general, there are 3 different ways of transmission. So one is simplex, and as it is actually clear from the name, this is very simple, and this is only one-way communications. For instance, once we connect this keyboard to computer, once we type, we can see some things appears, right? This is one-way communications. We are communicating from keyboard to computer, or from mouse to computer. But there are half duplex, which is the 2-way communication, but this is still limited because the communication cannot happen at the same time. And this is similar to walkie-talkie. So actually once one side is talking, the other one cannot talk at the same time. And the full duplex, which is very useful, so there is no limitation here. In both directions at the same time, we can have communication. And this is similar to telephone, internet cable, and everything that we are using. This is full duplex. And so, okay, this is the last things that before the break I want to mention. So there are some devices, some technologies. I don't know, anybody here already took the computer architecture course? No? Okay, in computer architecture, you can see the details of these devices. There are 2, actually those are some IC integrated circuits and are very well defined in the literature of computer architecture. So these called actually multiplexer or MUX. And the main role of this multiplexer is getting the different signals with different frequency, put together the signals, combine the signals, and the output of the signal is unified. You can see here we have n inputs, but only one output. And here, this multiplexing here is using this multiplexer. So we have one multiplexer in the sender, and they put together different signals with different frequency and come up with a unified signal. Now from one link, so this signal can be passed, and at actually this is the sender, and this is the receiver. At the receiver, we have demultiplexer, and demultiplexer, the role is completely other way around. So the input would be single, but the output you can see is n output in the number of n input. Now in the demultiplexer, the signal actually using this demultiplexer would be decomposed and split down to different original signals, and different original signals are recovered actually from this demultiplexer. And you can see, for instance, using this animation, so these are 3 different signals. So sorry. You can see the 3 different signals are putting together. So I'm coming here, and here again, those would be disassembled, and we have the original signals. We recover the original signal because those are the signals that we transferred, and we need to preserve the properties of those signals we want to use with the original ones, right? And this is, for instance, if you see at the TV, so there are three different colors behind the TV, and this is exactly multiplexer and demultiplexer for the audio services. And for each of one, so you can provide a cable, and now inside the TV, so this transferring is happening, and the rest actually is inside the TV. Okay, is there any question? So, okay, we can have a break for 10 minutes, and we can continue after that. Thank you.
Sorry for disrupting the class just now. Actually, I have a question for Mr. Exactly making. For this question, it says they want us to find the best case delay response for 40,000 kilometer away satellite, but in the answers that were given, it says packet sent was 4. So do we assume that the packet is 4 for like shipping? Can we assume any packet number, or must it always be 4?
So you already attended the...
I didn't know. I was sick.
That was the first session?
Yes.
Okay. So for the tutorial sessions, and my colleague is responsible for, so at the, I think after this class, I don't know,
Yeah,
half past, 1, right, or 3. So yeah, we can ask him because he designed these things. I can look at it, but this would be time consuming to see what is happening. But he know everything, and easily can actually guide you.
Thank you.
You're welcome. So these periods are possible. In the previous session, no, this is for this system, this is for the you see, those, yeah, these materials are some overview and concepts that we need to learn about. But if you are working regarding the exam, so the exam would be very similar to the tutorial. You already attended one session. I would suggest, because my colleague has some questions there, responding to each lecture and solve those questions there, and you can see if you can follow those questions there. So, yeah, posted, but yeah, of course, but even these materials are posted, but if you do in the class, especially that class, because he's solving and he's addressing the question of the student, and that was very helpful. But regarding the concept, just in the final exam, you have some questions or some drag and drop questions or something. You need to know the concept. For instance, okay, I can explain you some items, and I can see this is the responsibility of each student. You need to know. If you know, yeah, of course. Yeah, put here. Yeah, of course. But the main things that we are the main what is this ingredients, so those are the details of the label. Anything relevant to that, as I said, this is just relevant for you. Trying to know the whole thing, whole picture, and yeah, of course. but maybe the address is only data. Not maybe, I don't know. Not the same, but yeah, we just put procedure. Yeah, that's very important. And here the concept that what is the difference between these two layers? You need to do this one. So just if you understand what is the difference between all our physical this one, just put it down and see. Exactly. There are some restrictions. There are some solving problems. Now you need to say from including the go to satisfy some property that I asked for. For example, some multiple requests. What the example? I mean, it's not in the sense that the main goal here is to provide some supporting material and the exam is just for simple to make sure for us to follow an tutorial. So those are important. So just good for your cabinet semester you that I asked you who prices has the those are you already have the now you already know the concepts of must and figure out here once you learn the simulation path for your next simulation you can use it in the next course. Yeah, of course, my colleague at the very beginning of the session, 5 minutes ago, but unfortunately, Java is not now he's working in his own laptop and doing another transfer to his you have two courses prepared as you are working regarding the creating and the second one starts from the not even next to the next week. No, even next week. Starting from who is on the the time is very large. You have to have a very maybe it's not difficult, maybe it's a 100% exam. We are talking even this morning I exchanged so many. But is it good if it's not assessed? This is for your own, but why not assessed? But is it good again, a good practice to meet the deadline? Even without yeah, I know, but I will update you. Actually, I tried to do that. It's already accepted for 3 months ago. We already decided. Yeah, that is to take the last from 3 months ago. This is a week. You can even check this is on. But since you have time, actually, you pay for a year. Okay, let's continue with the sorry. Let's continue with the multiplexing concept. So, okay, we have two types of. Do you see my voice? Do you hear my voice? Yeah, but it's okay. So we have two types of multiplexing that are used for this task. So the first one is FDM. Here that stands for frequency division multiplexing. And the key point here is that it's working with the frequency for different frequency. So break down the signal to different frequency and transmit several signals using this multiplexer and demultiplexer that I explained. And take advantages of this issue that the useful boundaries of the medium that we are using normally exceed the required bandwidth of the given signal. But the second one that is very common, especially in mobile networks, so this is TDM, which is time division multiplexing. So the first one that was frequency, but here we have time division. And here, instead of working with the frequency, it is working actually with different times, sample the time with some notions of clocks. And now, but consider, of course, a very little time slice. So this could be even milliseconds. So during that time, in milliseconds, for instance, wants to transfer some data. And here, instead of useful bandwidth, is working with the data rate. So the bit rate or data rate of the medium normally exceeds the required data rate of the digital signal. And this TDM, for instance, one potential application is once we want to transfer a music or voice. So this is exactly is coming with this TDM approach. Or for instance, for controlling electric trains. So once the driver of the train is pushing the brake pedal, so once the signal here is transferring to control the train, and the technology that is used is again using time division multiplexing. But here to show you more details regarding this, for instance, here again we have the global system for mobile communication. And for this GSM, so there are 124 different frequency channels. So you can see for each channel the frequency is different. And each user is automatically allocated to one of these channels. So suppose here, for instance, one user wants to make a call, and one channel in the system is allocated to this user, right? So you can see each 8 slides here, which is similar to 8 bits. So here is called the TDM frame. Each 8 actually a slot here. And for each channel, for instance, let's say for this channel for one user, so this particular time here is called the one time slot, right? At this particular time, and here, for instance, you can see here, again, repeatedly at this particular time, the voice message would be transferred to the sender. But this happens actually in a very, very short time. So the receiver doesn't realize this is happening. So this sampling time would be very short. And now, but the procedure actually is like this. Or here, for instance, again here, automatically for this different time slot, so the voice message is transferred, let's say, from sender to receiver. And this is the application of TDM, is working with time instead of frequency in the global system for mobile communication. But regarding this transferring the data, so one thing that I will talk about this detection and correction of error, but another problem is bit encoding. And what is bit encoding? The bit encoding is sometimes we have some synchronization problems, right? For instance, once we want to send the data from one mobile to another mobile, so the clock of the two machines doesn't work at the same time. So never run exactly at the same speed, right? And the clock here means, I don't know, again, you are familiar with that. This is a notion in the computer architecture. And this clock actually is a notion of like the wave, square waves. And clock, at some points, clock is high, at some point, clock is low, and based on that, we can model the time. So this time, this axis here is modeled, and the notion of time always can be, in the digital platform, can be represented by the clock. And what the clock of the sender or receiver could be in a different speed, or even in a simpler way. So you can see, for instance, this is the signals that you want to send. So, but how many ones, bits are in the picture below? So this is a continuous, similar continuous signal, right? This is one, but we don't know for each time period, like here, how many ones actually included here. Or even once you want to transfer this signal, let's say 1100, so here, how much is the gap between 1 and 1? Or how much is the gap between 1 and 0? So all those questions are coming with the synchronization problem. And how we can resolve this synchronization problem? We need to go for bit encoding. And for bit encoding, one naive solution is to provide a separate clock wire to capture actually these clock informations once we want to transfer the data. But this is not a feasible solution for a long distance actually communications, right? Because let's say from here to another continent or actually another country, we cannot provide wire from here to capture this clock, what is happening. But if we are in a room where there is no problem, we can provide such a solution. But the permanent solution that is provided here is using different technologies, which is called return to zero technology and Manchester technology, and non-return to zero invented technologies. So using these three technologies, this is not technology actually, this is methods. So some convention that are again common in the literature, in the network communication are used. Using these three, they try actually to synchronize the signal once they are sending some piece of information. But here you can see, I can explain what is the details of this bit encoding using return to zero technologies, method. So for the return to zero method, so we would have three different levels. So previous time, we know that zero actually voltage would be shown by 0, and plus 5 actually voltage, we know that this is represented by 1 in the digital platform, right? We are working with binary. This is either 0 or 1. So if we are working in the computer architecture with, or in the network actually communication with 0 voltage, this is represented by 0, and plus 5 voltage is represented by 1. But here we have three different levels. And here 1 and 0, you can see, for instance, for 0 is called negative pulse and is called positive pulse. But in this return to 0, we have one intermediate voltage level, which is actually 3 volt. And this is represented by N, which is called neutral. So we have three different voltage levels: 0, neutral, and plus 5 voltage. And now this is the wave that we have in reality. And now we want to model this as either 0 or 1, right? And the rule here, the algorithms here is like this. So here, because we have increase here in this time interval, and this is this is represented by high voltage, because here the voltage actually is high. So we index 1 to this part of the signal for this time interval. But here you can see we have, let's say, 3 voltage. This is N3. this is the neutral level, and now here the signal is decreasing. So because this signal here, the majority is decreasing, now for the whole interval, we are indexing 0 to this part. And here, likewise, so the signal is decreasing, so we index 0, and here the signal is increasing, so we indexed 1. Now, instead of this signal, which is very oscillating, just we are representing this type of signal using this RZ as this. So 1, 0, 0, 1 for different time intervals that we are working. And this is, and once we send such a signal to the receiver, so this would be well recognized for the receiver, and receiver can analyze based on this piece of information that we are passing. So this is called return to 0. But another method is Manchester, which is very useful and very common in practice, so they are using. Here even the explanation, the procedure is simpler than the previous one, because instead of 3 different voltage levels, now here we have only 2 voltage levels. And these 2 voltage level is either 0 or 1. This is low voltage and this is high voltage, we already know that. And again, but here, instead of seeing actually this is in high voltage or low voltage, here only we are working with the age. And if the age of the signal is increasing, which is calling raising age, if we are seeing the raising age, this is raising age because signal is going from 0 to 1, right? If we have a raising age here, a rising age here, so we can put here 1 in the index 1, but here we have falling age, right? Once we have here falling age, so we index the actually bit here 0. And again here we have falling age, so we index 0. And here we have rising age, so we index here 1. Now if we want to transfer this signal, this wave actually, this wave piece of information, in the Manchester system, so this would be the representation, 1, 0, 0, 1. So in Manchester, there are only 2 voltage levels, and we are working with either rising age or falling age. As soon as we see the rising age, we actually assign index 1, and for the falling age 0. But if you see some textbooks, so this is other way around. So this is some agreement, right? So for some textbooks, so they are saying we consider the rising age as 0 and the falling age as 1. And this is, again, correct because this is some agreement. But the main things here is that no matter we are using which representation, but we need to stick to that representation until the end of the process, end of the analysis, right? If you are, it's saying actually in the computer architecture as positive logic or negative logic. This way that I explained, this is positive logic for rising 1 and falling 0. But someone may be saying, I would like to work with the negative logic. And this is also well defined in the literature. And what is the difference? There is no difference, but some guys are, because once here, if you see the signals, once here is actually more repeated than 0, because once means that we are working with high voltage and the consumption of the circuit or network is high, and this is more repeated. But some guys are saying, okay, I am actually, I would like to work with 0 instead of 1, because instead of seeing many 1s, so this is more easy for me to do the analysis using 0. So, okay, he can work actually with the negative logic, but the outcome would be the same. So there is no difference. And this is the last method. So non-return to 0 inverted. And this method is saying if this is the original wave that we want to analyze, we want to send actually to the receiver. So the only things that we are caring about is the changes, no matter these changes is rising or falling, okay? Once we have changes here, there is one change here, right? From 0 to 1, but we don't care about it. So there is one change, so because of this change, this would be 1. But there is no change in this time interval, right? So this would be 0, there is no change would be 0, but there is one change, although the change is from 1 to 0, we don't care about it. So we need to put here 1 as the logic of this NRZI method. So in the previous one, we needed to detect these changes rising or falling, but here simply any changes actually results in 1. Otherwise, if there is no change, so this could be 0. And this is for instance, once we send the information using this approach, so the receiver already knows that. So this piece of information that we are sending as 1001, this is the outcome of this NRZI method. And based on that, provide the rest of the analysis. But talking about these bits, one thing that is very important that you need to actually learn about it is error detection and correction. And what does it mean? This means, for instance, if we want to send this piece of information from place 1 to place 2, from sender to receiver, so okay, the information here is a sequence of 0 and 1 as expected because we are working with the binary variables. But how we can ensure that, so the receiver would receive the same 0, 1, 0, 0, 0, 1. Maybe some of these binary variables is flipped and changed to another one, right? This means we are sending some information, but the receiver receives some wrong information and do the analysis using this wrong information. And we want to prevent this issue here. So for that, so first we need to detect the error. Is there any error once we send some piece of information or not? And if there is an error or two errors, where is the location of the error? So we need to detect the location of the error. For instance, this error, if, for instance, the receiver receives so this piece of information, so this means actually one error happens, and the location of the error is in the 3rd bit, and so needs to be corrected. So first, the location of the error should be detected, and then so this error should be corrected, right? This is called the detection and correction of the error. And how we can do that? One notion, mathematical notions that is used is Hamming distance. And Hamming distance by nature is used for the strings, not for the binary variables. But we extend and utilize the notions here in our setting. And what is saying Hamming distance? So Hamming distance is saying once we have one string, let's say A, B, C, D, and once I want to transfer this string to another place, so suppose now we have A, B, D, C, right? So now for Hamming distance is saying actually for each place of these letters, for instance, this is the first place, right? We need to do the comparison. These are the same. This means Hamming distance is 0 by now, right? The second one is the same. Hamming distance again is 0. The third one is different. So Hamming distance is 1. And the last one is also different. Hamming distance is 2. So simply saying the number of the positions that these letters are changed, actually. This is Hamming distance, shows the Hamming distance. But we can use this even in the binary things, right? For instance, here, this is the original message that we want to send, but this is the one that receiver actually received. You can see here, one change here happens, right? And this means the Hamming distance of this transformation is 1. There are other representations for Hamming distance. For instance, the minimum number of substitutions required to change one string to another one exactly is the same things that I was talking about, right? Or some things based on error. Again, this could be another representation, but the idea is this. Just you need to check each bit, corresponding bit to each other, and see is there any changing or not. And here you can see the relation between Hamming distance and error detection and correction. And what does it mean? So this is the Hamming distance, h. And here we have some valid code word. So what does it mean, this valid code word? Is the sequence of binary, the piece of information that we want to transfer. Could be anything, right? So suppose I want to transfer this one. 1, 1, right? this is a valid code word. This is valid by default because this is the original message that I want to transfer. No matter this comes from where, no matter this represents voice or video or anything else. So this is the message that I want to send. This is valid because this is the one that I need. And once the Hamming distance is 1, what does it mean? This means there is one error in this sequence, right? So suppose this is the problem. Suppose the last one has the problem, right? Now the Hamming distance is 1, but by this Hamming distance 1, the computer is not able to provide the error detection. Why? Because once this 1 is changing to, this 0 is changing to 1, is flipped to 1, now the original one, so would be this one, right? And this is exactly the original one that we wanted to send. So this means once the Hamming distance is only 1, because there is only one error, by flipping that bit, we can reach the original one. And this means no detection by the computer we can have here. So here we don't have any detection, but if the Hamming distance is 2, this means 2 bits have the problem, right? Once we actually flip one bit, we will reach another string. Still, this string actually is not the original one, right? Because again, one bit still has the problem. Now this is invalid code words, right? But by flipping the another one, so we can reach the valid code word, which means the original message that we want to actually pass. And also for 3, so we would have 2 actually errors, and for 4, we have with the same procedure 3 errors. So in general, we can say if we want to detect D errors, the Hamming distance should be greater than or equal to D plus 1. This means if we want to actually detect 3 errors, the Hamming distance should be at least 4, right? And we can see here. So if Hamming distance is 1, this means the error detected would be 0. So because by flipping that one, we can easily reach another string, which is the original one, and we cannot continue actually by that. So these are some notions, but in the following, I will show you how we can detect that. And this is for detection of the error, but there are some things, okay, after detection, now how I can correct the error, right? So for the correction of the error, if we want to correct the error up to D errors, the Hamming distance should be greater than or equal to 2D plus 1. And if you see the literature using the same procedure, you can see for correcting the errors, now you need the Hamming distance actually to be 2D at least plus 1. But those are some fundamental notions. The things that is very important, how I can correct how I can detect and correct the errors. So there is one terminology which called parity bit. And what is parity bit? So suppose we want to send this information from sender to receiver, right? This is a 7-bit information, right? Each bit could be either 0 or 1. Parity bit is an extra bit, a redundant bit that you can call this a virtual bit. A virtual bit that once we want to send some piece of information, we add this extra bit. Later on, we use this extra bit for the for the sake of actually detecting and correcting error. So if we want to send this 7-bit information, so this bit that we intentionally actually add this bit is called parity bit. And the parity could be either even or odd. So what is the difference? Again, there is no any difference. For establishing that there is a difference, I explained. But in general, this comes with the convention and agreement from the beginning. You want to work with the even parity or odd parity. In literature, so this is common, works with even parity. But the outcome would be the same. So this is up to you. But what does it mean by even parity? So suppose this 7 actual bit that we want to transfer is like this. This is given. This is not in our control. This is given, and we want to transfer this actually sequence of 0 and 1 to receiver. Now we need to, for defining this even parity, if we want to work with even parity, so we already at some location But what is the value of this location? Could be either 0 or 1, right? This is binary. So should be 0 or 1. So if you want to work with even parity, you need to count the number of ones in the sequence that you want to actually pass on as the information, right? Now the number of ones here is 4, and 4 is already even. If we want to work with even parity, we put here 0 because the whole number of ones should be even if we want to work with the even parity. But if we want with the odd parity, if we want to work with the odd parity, so here you can see the number of ones is 4, and this is even. Because the parity should be odd, this is some agreement from the beginning. Because this should be odd, so we actually add 1 here such that the number of ones would be odd. So in summary, the parity bits is some extra bits later on would be useful for detecting and correcting errors. How many parity bits we need to add? So we have some closed form formula for that, I will show you. But what is the value of this parity, 0 or 1? So it depends, you want to work with even parity or odd parity. So suppose in this lecture, we want to work with even parity. Just simply count the number of ones in the sequence of information that you want to pass. If this is odd, so you need to put parity 1 to be even. If this is even, so it's already even. Just simply put the parity as 0, similar to here. But here you can see the table that is useful. So in general, so this is the length of the information that we want to pass. So if the length of the information is 4, this means the information that we want to set consists of 4 bits. Could be 0 or 1, no matter, this is given. If the number of this information is 4, how many parity bits we need to add for the data detection or correction? This would be 3. Comes from where? So there are some analysis. They already did that analysis, and now they know that for this for an information with this length, actually 3 check bits here is exactly parity. So 3 parity bits needs to be added. Okay. What does it mean? This means if we want to send such an information, suppose this is 1100, the sender automatically add 3 other bits as the parity bits automatically, because in the receiver those extra bits would be useful for detecting error. But what is the value of this, 0 or 1? So later on we can decide about the value. Now the total size would be 7, right? And the percent overhead, so this is 75%, which is simply actually the check bits that we are added with the whole size, original size, which is 75%. But if you increase the word size, you can see, for instance, if you want to transfer an information with this size, so this is the number of parity that you need to add. But once you reach this size of information, which is a very huge information, you can see the number of parity is not increasing too much. And this is the percent. You can see the overhead percent would be only 2% for a very big information. This means actually the relation is not linear. This is a logarithmic relation. And you can have this table. And once you have some information with this length for transferring, you can see how many parity bits you need to add to continue. But to show you actually what is happening, so suppose for the first one, suppose we want to, in this lecture actually, I show you first one and also this one, but this one is, you can easily generalize this one for any other lengths that you want to continue. So, okay, here suppose we want to work with the information of 4 bits. And suppose this is the information that we want to pass, right? This is 1100. I want to show you, I want to explain to you the algorithms. But here, because we are working only with the 4 bits, so we can visualize this using these circles. But if this is more than 4 bits, this is not possible for visualization. But for 4 bits, So the things that we are doing is, we already know that the length of this is 4, right? We already know that from this table, the number of parity bits that we need to add is 3, right? Okay, we add 3 here. Actually, this procedure that I'm explaining would be done automatically in the sender part, right? But I'm explaining actually what is happening in between. So here, 3, we know that 3 parity bits should be added automatically to this length of information. Let's call those actually A, B, and C, okay? A, B, and C. And the thing is that the procedure is that for each parity bit, we need to draw a circle, okay, for each parity bit. For instance, here, this is A, we draw this circle. For B, we draw this circle. And for C, we draw this circle, right? And because between 3 circles, so there are 4 intersections, so these 4 intersections actually is the place of these 4 actual value that we want to, actual data that we want to send. So let's put this data in this way. No matter you are putting in which way, this is up to you. But let's put in this way, 1100. This means actually this is the data that you want to send. Okay, now we need, in the middle part, we need to decide about the value of A, B, and C. And again, up to here, just we are talking about sender. So later on, we will talk about actually receiver. But here, this is the sender part, right? So this circle is corresponding to A, right? And what is the parity of A? So we need to see the values of here, 1 values here, in this circle. The values of 1 in this circle is 1 and 2. This is already even. So we put here 0, right? Based on the even parity that I explained, because we want to keep this even. So this means A here would be 0, that we already put here. So what about B? B, the number of 1s actually is 2. Again, we put here 0. We want to keep it as even. B would be 0. And C also here, the number of 1s is 1. So we put here 1 because this is odd and we need to convert this to even, right? Okay, now we have the value of these parity bits in the sender part. Now the sender established everything and sent this piece of information with the 3 extra values to the receiver. So this is the sender part, and this middle part is also for the sender part. Now this is the receiver part, the right-hand side. And suppose the information in the receiver part is received as this. If we compare this information, actually this is the one that we sent, right? This is the one that we sent, right? Wanted that we sent, but this is the information that we got from the receiver. If you see one actually bit here, there is a problem. Here that was 0, but here is 1, right? But how this would be detected from the receiver side? So the receiver, again, for each parity, is seeing actually how many 1s actually there are in each parity. Here for A, there is 3 1s, which is odd. So this is a red flag. So this means there are 1 problem in this circle. Already we know that. The receiver knows that because of this, again, even parity agreement. What about this C? Again, C here, 1, 1, 1 is odd. So again, there is a problem here. So this is a red flag here. But what about B? B already is 1 and 1, and this is 2, so this is okay. So the receiver now knows that actually the circle corresponding to parity B is fine. This is already even. But A and C, there are some problems here. And how detect the location? So for a circle A and C, take the intersection between these 2, but excluding B, yeah, right? Because B is already fine. So if you take the intersection, so this would be the whole intersection, but excluding B means there is no problem here, the problem would be here. So the problem would be here, and the location now is detected by the receiver, and the way for actually detecting, simply take the intersection between the circles that are problems and exclude the ones that are fine. Now the location is detected exactly the location that we had problem. But how to actually correct this? There is no possibility, right? Just this is 0 or 1, right? Because the current one is 1, so simply it would be changed to 0. And this is the original one that we have. Or this is 0, simply would be changed to 1. So for correcting the error. Is there any question? Okay, let's practice with another ones to see how this procedure actually works. Okay, suppose we want to transfer this information here, 1, 0, 1, 1. You can put anything that you want. Okay, this is the original information that we want to send. So first we need here to define the parities, right? The parity of these two would be 0, because this is already 1 and 1, right? This is 0. The parity of these two, again, this is 0. Okay, I can put the original one first. And the parity of these two would be again 0, right? Because all of them are odd. And suppose actually here, for instance, we have 0, 0, 0, so 0, 0, 1, 1. Suppose this is the one that is received actually by a receiver. This is sender part, this is sender, and this is receiver. Suppose this piece of information is received by the receiver, right? Now the receiver is checking what is the problem here. Is there any problem with A? Yes, there is a problem, because here this is odd, so there is a problem here. What about, is there any problem here? There is no problem? Yeah, of course. And what about here? Yes. Yeah, there is a problem here is odd. And now this means we need to take the intersection between these two, but excluding C, which the intersection would be here, right? And here actually exactly we have the location of the error, and just by easily flipping this to 1, so we would have the correcting that. And this would be, if you, for instance, see the IC for implementing this would be very simple implemented. So using an XOR gate, which is some basic gates in the logic implementation. And this, for us actually, I'm trying to visualize the things, but for the computer, very easily so would be detected. So suppose we want to another example. So for instance here, this is the information that sender we want to send. So first we need to decide about the parity. So parity here is odd, would be 1, here 1, here 1. And this is receiver 1, right? And suppose this receiver actually received as this. Now for this guy, so we can say, we can see actually here, this is already odd, so there is a problem here. So this is odd also, there is a problem here, and this is odd, there is a problem here. This means take the intersection amongst the 3 circles that we have, and this is the intersection, and this is the place of the error, and for correcting the error, simply we can flip the bit from here, this is 1 to 0, and we can go for this one, right? But this is just for 4-bit numbers. How we can generalize this to more bits if we have piece of information more than 4? So suppose here I want to show you 16-bit, but you can easily generalize the idea for any number of bits that you know. And this is, because this is more than 4-bit, we cannot visualize here. Just we are working instead with some tables. And here, the number of actual data that we want to transfer is 16. Based on the table, we already know that for this 16, we need to add 5 parity bits. We already know that. And this is the location of the parity bits. There is a template for each size of the data that we want to transfer. But if you want to see the location, how we can reach the location, this is 2 power 0, first location, 2 power 1. So 2 power 2, which is the 4th location, 2 power 3. So this is the 8th location, and 2 power 4. So this is the location of the parity bits. But, okay, now we have the locations, but how we can decide about the value of this parity? Could be either 0 or 1, right? Remember the circles that we had? With the circles, actually, we could, before sending in the sender part, we need to decide about the value of those are 0 or 1. So For deciding this, so we draw a table, and in the table, the column of the table is the number of the whole bits that we want to transfer. The number of whole bits is 21, we know that. So that's why we have 21 columns, right? But what about the rows? So the rows would be the number of the parity bits, because here we have 5 parity bits, so here we would have 5 rows. And we can actually put this, the first one as 2, 0, like there, 2, 1, 2 power 1, 2 power 2, so 2 power 3, which is 8, and 2 power 4. And now the procedure is like this. So for each parity bit, we already know that this is corresponding to the first parity bit, right? The row of the table. But for each, in the table, we need to put some marked as, let's say here, check mark. And later on, we only care about the values of these mark that we already provided. But I will explain this. But here, how we can realize this marked in the first row of the table, in which places we need to put. So this is very simple, because this is 1. This is the first actually row. So this means the first entry of the table should we put the mark. And for the second one, we jump over. Again, we put 1. For the second one, we jump over, so on and so forth, right? This is for the first part of the table. The second one, we know that is corresponding to the second parity bit. So this means start from the second, which is here, put 2 marked, because we have here 2, and jump over 2 of them, right? Again, put 2, and jump over 2 bits, and we can continue. For the third one, so this is corresponding to 2 power 2, which is 4. Start from the 4, location 4, put 4 of them, and jump actually for the 4 empty bits, and again put 4, so on and so forth. And 8 here, yeah, you know about this procedure. Starting from 8, put 8 of them, and you can continue, and for the 16. And that's why I'm saying now you can easily generalize the notation to any number of bits that you need, because just you need to establish such a table. Now we have these checkpoints, and we want to decide about the value of these parity bits. For the first one, we know that the first one here is corresponding to the first parity bit, right? So now, because we already know that, we already have these check marks, just we need to count the ones in the information that are corresponding to these check marks. Now we have here 1, 2, 3, 4, 5, 6, only the ones that are corresponding to these check marks, right? And because this is already 6, this is already even, we put here 0. Similar to the circles that we visualized, right? For the second one, so we know that this is corresponding to the second parity bit. Again, we need to actually care about these values. How many ones are there? Again, this is even, this is 6. Now we can put here 0, right? But this is already even. So for this one, so we need to care about this. Again, this is even, so we can put 0. For this one, so this is 1 and 1, this is 2. So again, we put here 0. And for the last one, so this is 1, 2, and 3, and this is odd, so that's why we put here 1. The value of the parity that we are adding. So this is clear, the procedure. Do you have any questions for the procedure? If this is not clear, yeah, we can ask. So, okay, now for the sender part, we have everything ready to be sent, right? Now we know that how many parity bits, where is the location of the parity bits, and what is the value of the parity bits. So the value based on this table is completed, and now the piece of information is ready from the sender part to be sent to the receiver part. And suppose this is the receiver, and the receiver receives such an information. And if you compare this piece of information from receiver side to the sender side, you can see there are one problem here, right? One bit here, suppose, has the problem, and the problem is here. Now the issue is that how the receiver can detect the location of the problem and correspondingly correct the problem. So the procedure is like this. So the receiver, now we are talking about the receiver side. This is similar to the right-hand side of the circles that we already visualized. So the receiver first look at the first row for this parity, and they look at the information in these marks. So here and see how many ones are there. And once we see here 1, 2, 3, 4, 5, right? This is 5 ones, means this is odd. And this means there is a red flag here. So there are one problem regarding the first parity bit based on the receiver that is counting. What about the second one? The second one, the same procedure. This is 1, 2, 3, 4, 5, 6. So this is already even, so there is no problem here. And here again, you can see 1, 2, 3, 4, 5. Again, this is odd. There is one problem here. And this is also problem. And for this one, so you can see 1, 2. So there is no problem here. And the last one, there is 1, 2, 3, 4. This is again already even. There is no problem here. So by the receiver is detected at this row. So the number of the ones is odd. There is a problem here, and at this row, these rows. And how the receiver, based on these two rows, can detect the location of the error? So simply add these two together. And if add these two together, so we will reach 5. And from here, if we count 1, 2, 3, 4, 5, this is the location of the error that happens. And if we see the original message that would be communicated, so you can see it exactly in the location 5. So this error happened. Now the location of the error is clear for the receiver, and how to revise this, because this is 0, just simply flip this from 0 to 1 and correct the error for this 16-bit number of bits for the information that we want to send. But you see, this procedure would be very fast, and once you want to compare two computers to each other, so this is regarding the precision of the error correction. So if you see the manuals of the, for instance, processor systems of different machines, you can see this is written, how much is the precision of the detecting and correcting errors. And this would be corrected automatically. For instance, once you want to copy and paste one piece of information in your computer from one folder to another folder, so you can see the exact information would be passed, right? You don't see your for instance, transferring one Word file, but you see another PDF file. So this is not happening. And this is regarding this error detection and corrections, because this is automatically is done, especially in the new generations of these processing elements of the machines. And those are some very important part. And even in communication networks, actually, this is useful, because again, we have two parts, sender and receiver. And for transmission of any data, we need to make sure there is no error once we want to transfer in the data. Okay, is there any question? Okay, so we can stop here, and next week we can continue actually with the main lecture. Thank you. Yes.
It's you.
No, practical is the tutorial and practical. Have you ever tutorial? Yeah, Pedro would be there with the other. And he would actually solve some question sets for you. So the type of the exam is very similar to the tutorial. If actually you consider some parts of the exam as a question for solving, but there are some parts of the questions based on
explanations describing what is the difference between this layer and that layer, and those things you can actually have this based on the materials of the main layer. But in the tutorial on top of it, using the material of the lecture, so some specific questions will be solved, and if you practice those questions and if you follow those questions, so everything is good.
Hi.
Hi.
How are you? Good.
Oh, you will record the video. You record the audio. For this one? Oh, you will this one. Okay.
I was told them you guys, right?
Yes, you can actually practice it. Yeah. Okay, please try it out. Oh, I know actually. Yeah, but of course, in the next lecture, I actually talking maybe not the case.
I'd say Dan has got quite good at so it might be worth it. But yeah, it's
No. This was
not you.
yeah, of course, this is not the case. Even I got distracted at some point, but I thought we are talking about something scientific. Okay, I thought the class would be relaxed, but if this is very no, that's fine. This is directly myself. But I thought this could be more relaxed and the students are listening, but if at least one student is saying that it's disturbing, so of course.
All my friends say it's fast.
Yeah. Okay.
Sorry about that.
No, that's fine. That's fine. No, that's fine.
So about the module, so I'm not sure what should I focus on the study. And I'm not
For
sure.
the exam?
Yeah.
For the exam, so you need to follow.
Is there going to be exam? Is it for certain?
For what?
Is there going to be exam?
Yeah, for exam, you need to follow the tutorial.
Okay.
But you know, if you don't know the concepts of the class, you cannot. So first you need to learn about the concepts of the class.
Yeah.
But for instance, if you don't have any question sets for the error detection in the tutorial session, most probably this is not engaged.
Most part of the in the lecture won't be in exam.
In the tutorial. So here I covered, or my colleague would be covered the majority of them. But some of them specifically we start covering the tutorial. Those are the questions of the exam.
Oh, okay.
You need to have to learn about this material.
Yeah.
But if you want to prepare yourself for exam, like a mock exam,
Yeah.
so you need to follow the question sets inside the tutorial session.
Okay.
Because Pedro there solving many problems, and those problems are the structure of those problems are very similar to the exam.
So what about the content in the lectures? Do I have to fully understand everything that
This is an overview, yes, but sometimes maybe some questions of the exam would be describing, so explanation. For instance, explain what is the difference between this layer and that.
that will also be the exam as well as topics.
So this is the high level explanation. We need to, these are the main structure of the
Like a basic, like a fundamental.
This is very fundamental. But sometimes you're saying, okay, what is the high frequency here? Different. No, you don't need to memorize those information. Those are informative, right? you don't need to bother yourself. But some things are fundamental for describing. Yeah, of course you need to do that. Apart from that, we have some actually question sets in the tutorial. Those are very important. So
Is there going to be like the calculation of the binary to the hexadecimal?
if we have such a thing, yeah, you need to actually practice it, okay? But if you don't have such a thing in the tutorial, so most probably this is not the question of the exam. Because you know the main goal of the tutorial is to prepare the students for the exam.
Yeah.
If that question should be repeated, so in the exam, so in the tutorial you need to actually provide the solution, practice. But there's some things here, for instance, this error detection in this level, so could be informative. This is good, you will know that, but maybe in the exam, this will be time consuming.
I see. Okay.
Or for instance, for converting bases to each other. So for converting bases to each other, this you would have another course module called the fundamentals of computing. And this is the main questions of that course, not this course. There are some things more important here, right?
Yeah.
So you can actually follow the question set of the teacher.
Okay. So have you decided yet? Will the marking will be exam and coursework and half and half?
Most probably would be 100%.
100%.
Because this is the current mark of the course, right? MOF, if you Google, so at Newcastle, you can see this is already decided even before you take the course.
Oh,
And that was online.
it's already been decided.
Yeah, for any course. Actually.
So it's not up to you.
So this is not up, this comes with some committee and teaching team, and they decide based on the actually module leaders of the course, but previous one. So previous one, I'm the module leader, but for the current one. Previous one decides for the next. I can pass, for instance, my experience to that team, and for this half and half, this would be very easy for the next team.
Okay.
So, and you know this MOF is very defined, and many students know that. And once they want to take the course, they see what is the assessment method. And based on that, decide should I take the course or not. And based on the mark, so that was 100% to begin with. But we are trying to make it actually more relaxed and better for students to be half and half, but this is not guaranteed. But I will update you.
Oh, so it's not decided yet?
No, of course. This is decided, but we want to change that.
Oh,
But this is not decided.
you're not sure if you can change it. Oh, okay.
This is a very, very, very...
So I saw a coursework one uploaded yesterday, which deadline is December.
Yeah, I know. But if this is 100% for based on the exam, those coursework should be informative. Still, you need to follow the deadline. But if you miss the deadline, you won't miss any mark. But this is good, you meet the deadline, but it's a good practice for your career. Not after exam. For the next semester, you have another module. So automatically, so you can meet the deadlines and you can and you have some pressure before the. This is a good practice.
Will the exam related to the coursework?
I don't think so. But the coursework is regarding simulator. The exam is regarding some description, some solving.
And more related to the thing that the TA taught in tutorial?
Yes.
Okay.
In any module this happens. In any module, the main role of TA is to prepare the students for it.
Okay. Thank you very much.
मुझे वापस से पूरा CSS के साथ अपना साइट